The die, as we talked about, the die head assembly as such is the one that dictates the eventual profiling or shaping of the product, of the polymer melt or the plastic melt. So the main function of the die orifice is to develop the geometry in a profound way, that and in a systematic and then in a continuous regular fashion, that you can collect the products without any interruption. Common die profiles that you see in an extrusion system are solid profiles, hollow, wire or cable coating, sheet and filaments, or film or even filaments. The cylindrical filaments that you see or strand dies that you see basically are round solid profiles that come out of it. Again, solid profiles can be also the straight extrusion profiles, which can be used for decking and those kind of things. That's also what we call. But filament or round filaments is basically the strand die. So people call it in different ways. So the regular shapes could be round, squares, or rectangles, or even hollow rectangles. A lot of different things. Again, a hollow rectangle or a rectangle shapes could be the common decking material that you can see in outdoor applications. Some of the irregular cross sections could be some structural shapes and door and window moldings, and some of the other examples that you have seen in co-extrusion, those could be some irregular shapes. The automobile trims can also be some of the irregular shapes, or house sidings, and even some of the windows sealant arounds or the external profiles. Basically, that also can be categorized under the window moldings. They all can be. Okay, I'll start from the beginning. I think I'm saying the same thing. Let's take a deeper look into the die design that we have so far peripherally touched upon. As we talked about, die is a very interesting and most important component of an extrusion system outside the barrel, because the barrel is the one which makes the entire polymer melt, but die is the one which shapes it, which the consumer experiences. So the shape of die orifice determines the cross-sectional shape of the extruded based on the geometry that you're looking for. And some of the most common die profiles are solid profiles, hollow profiles, wire and cable coating, sheet and film, as well as filaments. An example of sheet and film are your Ziploc bags that are also extruded, and filaments are the ones which you saw in the video, the strands that come out of it and then that we have chopped off. And solid profiles, a good example for that is the decking material that's used in outdoor fencing and decking kind of applications, the rectangular shapes. So some of the common shapes are rounds and squares, but again, rectangle becomes part of that as well. Some of the irregular shapes could be some structural shapes or door and window moldings. The example that you saw in co-extrusion is one irregular shaped die or geometry that can also be extruded. And automobile trims and house siding are also other examples that can be extruded. So the die has a host of subcomponents within it. The extruder, of course, the barrel, you have the extruder barrel, and then the metering section, and the entire die assembly starts, right? And you have screen pack, which we have already seen, and you have a breaker plate. In the case of composites, you tend to remove the breaker, the screen pack, because that might clog and then it might create a lot of higher pressure issues as well. And then you have the dry orifice, and the orifice design is dictated accordingly, and through the orifice you get the solid material out. If you're trying to make a hollow profile, then of course you do have a mandrel as well, that and the material passes through the mandrel, and then you get the hollow profile. And there are a lot of examples for that. The extruded pipes are a classic example, where you have the hollow section inside. But all the products that you are seeing in the pictures are actually extruded either through solid or through foamed processes. In terms of wire and cable coating, the polymer melt is applied to the bare wire as it pulled through at a high speed through the die. So that means it's kind of like a co-extrusion, but it's not a co-extrusion because you don't have two different materials. You actually have the wiring system, and then the polymer is fed through it, and then you pull both of them together through the die orifice. That's how you coat the polymer on the outside, and you have the inside copper wire. And in the slit die extrusion of the sheet and film, basically the polymer melts, comes through, and then it spreads out, and then you can make the sheet out of it. The Ziploc bags are a classic example of this particular application. The polyethylene is actually extruded as a sheet, and then you get out of you get it out of the slit die or the sheet die. And in some people, you can even call this as a ribbon die, because you can extrude sheets as ribbons as well. Blow film extrusion process is just a variant of this. Basically, you have the polymer melt coming out, extruded out of it, and then you run it through the blow filming process, and you can actually do extrusion of tubes and all these things using this particular technology. And this is again a variant of the blow molding, which can make rigid parts, but this could be more flexible parts. What are the characteristics, design features of a die? That there are some ideal features, and then there are a lot of material considerations, and then there are some property portfolios that we have to understand when it comes to the die design as such. The ideal die features are provide uniform exit velocity across the die exit to balance the melt flow. As I said in the previous slides, maintaining a homogeneous and proper, accurate, balanced melt flow within the barrel is very crucial in terms of maintaining the melt quality, as well as the quality of the polymer melt, as well as the stability of the melt quality, as well as the melt stability. But exiting that through the die is embedded within that particular statement, because once it comes out of the die, that is when you see the product quality being enabled, or into and subsequently tested. So maintaining this whole thing within not only until the metering zone, but beyond that within the die assembly is also part of the die design process. And achieving a flow balance, whether through the pressure drop, so that the throughput is consistently maintained, is also another important feature of the die. And streamlining the flow, so that you don't see a continuous flow of material and stop it and then flow, stop it, flow, like that. But streamlining this whole thing is also another important feature of the die. Stagnated flow may lead to thermal degradation of the plastic melt, so we need to ensure the die design in such a way that there's no stagnation, and this could happen especially in terms of in fiber volume fraction of fiber composites, where higher fiber volume fractions may get stagnated at the screen stage. So the screen size and everything has to be accordingly designed and then put in, and in some instances we may even have to remove the screen. But of course, always having a screen protective layer is pretty will also give consistent viscosity and then flow pattern for the material through the die, and eventually through the product. Some of the material properties that are considered, of course, shear thinning, which is again a characteristic of the polymer being experimented or subjected to. But flow is a very sensitive to slight changes in the die geometry. So understanding the extensional flow, viscosity, and everything through rheological studies is very important before you even look for an application of the material within the extrusion technology. So understanding the overall viscoelastic properties of the polymer. So if it is standard polymer like polypropylene, polyethylene, ABS, and nylons, and all of these materials, which are very standard, very common, very widely used, all these things, material considerations are already well established and well built. So all that you have to do is just refer to the literature. But if you're developing a new material system, then you again have to understand this whole map, and accordingly make informed decisions in terms of the die designs. These are some common examples. Again, films, we refer to that as anything thickness less than 0.01 inch. Sheets are basically much thicker. Again, profiles are much thicker, and a good example of a profile is the decking material which I mentioned to you. And tubes or pipes, pipes is the hollow thing, tubes are the solid ones. Both can be extruded. In some ultra high molecular weight considerations, the tubes are actually RAM extruded as well. Ultra high molecular weight polypropylene or polyethylene, those kind of materials. One important aspect of profile extrusion dies is basically you don't want to exactly have the same dimension geometry of the die as such as the product. For example, let us say if you're making a square, you don't want to have four, and if the square is 4 inches square, right? So you don't want to have a 4-inch square exact dimension die profile if the product is also 4-inch square profile, because there obviously always will be die swelling. That is a common feature in any plastics. That means once the material comes out of the die, it starts to swell, and that's an inherent material characteristic. So as such, you would like to design the profile in such a way that even if there's a die swelling, the output geometry exactly matches your product geometry. So having some kind of exit shape as you see in the picture is very common, so that you can get the exact product shape that you are envisioning. And there are a lot of simulation packages that actually can simulate this before you go for actual experimentation, because you don't want to spend a lot of thousands of dollars in designing a die and to find out that, oh, this is not the correct one. So you can actually first do the simulation, understand the whole thing, and then go for machining of the die or fabrication of the die, and then test it out. These are some examples of die profiles that are good and bad. And as you can see, these are some open profile dies which are not good because they will have irregularity in terms of the cooling patterns. But again, those are the irregular shapes, and then how you can actually enable much better cooling system is basically what's shown on the right hand side picture. You can see the difference between the poor design of the die as well as the improved design of it. On the left hand side, you will see on the top A, it's an open profile system where on one side you have a very thick solid block. So the cooling profile, the cooling may not be so much uniform compared to the open profile where the top surface is exposed to the air. So the cooling on both sides may not be exactly the same, which means that obviously on one side you will have higher rate of cooling, on the other side you may have lower rate of cooling, which results in dimensional instability. So that's why you have an improved design as such. And again, on the B side also, you will see the same thing. So one thing you have to keep in mind is when a material is coming out of the exit die, a simple rule of thumb that you have to follow is the thickness across the entire cross section should be very much uniform. You shouldn't have a thick and thin sections that will cause instability in the dimensions as well as the whole instability in the product quality. So what are the rules that we can develop for the die design? Achieve a balanced melt flow exiting the die. That's a first and fundamental rule. Minimize the pressure drop as much as you can, so that you don't have die instability issue or material instability issues beyond the once the product exits the die. Provide flow control devices in the die to optimize the flow distribution, so you can monitor them and you can control them. Streamline the die flow passage to avoid flow stagnation areas. Again, that is very important, especially when you are compounding high viscous materials, or even in the case of fiber reinforced composites. Of course, the die assembly has to be pretty easy, convenient for the user. That's also very important. And the die landing length should be at least 10 times product thickness, so that you can facilitate lower melt stress to the polymer, and there's enough good relaxation time that you give for the polymer melt that comes out of the die. So that means the die landing length is basically, if let's say your product thickness is 1 inch, your die landing thickness should be at least 10 inches. That way you're giving the material, because it builds a lot of stresses during the barrel. Because if you think about the barrel, in the barrel you have uniform gap in the feed zone, and then it's being compressed in the transition zone, and then again you have uniform in the metering zone. So because of its variation in the compression that it provides at multiple different zone, it develops a lot of stresses, and within the die you need to ensure that all these stresses are relaxed so that the product that comes out is pretty stable, and it's the quality is not compromised. So for that, the rule of thumb is, if your product is 1 inch or whatever dimension, provide 10 times more for that in terms of the die landing length. And as I talked about, avoid thick and non-uniform sections. In fact, having thick and thin within the same die, within the same product, is also going to cause you these kind of instability issues.